Pattern matching. Pattern matching in computer science is the checking and locating of specific sequences of data of some pattern among raw data or a sequence of tokens. Unlike pattern recognition, the match has to be exact in the case of pattern matching. Pattern matching is one of the most fundamental and important paradigms in several programming languages. Many applications make use of pattern matching as a major part of their tasks. In this report, we will talk about pattern matching or the substring searching using brute force algorithm, not Morris pattern matching algorithm, Rabin-Karp algorithm, and Z algorithm.
This pattern matching algorithm will find a particular pattern from the given string. If the pattern is in the string, the process will continue. But if the pattern is not found in the string, then it will return to 0. For example, this is our string and pattern. The length of the string is 9 and the length of the pattern is 4. The formula to get the maximum number of time to reach the end of the shifting is number of the string length minus the length of the pattern plus 1. Since the length of the pattern is 4, it will be compared to the first 4 of the string. If the pattern is not the same, it will be moved to one place to compare it again. The process will be continued until the pattern is matched to the string. If at the place where we can compare the pattern are still not same pattern, then there is no successful pattern searching. So this shows how many times the pattern can get shifted, and this will tell the number of times of comparison.
Not Morris Pratt pattern matching, also known as KMP search, can do a substring search in O m plus n. Now, I will explain how KMP search will work. In this case, we will compute the suffix and prefix and what point to start. This to check if there is a mismatch in the character between text and pattern. Here is the pattern. This is the J and this is the I. If it is not same with J, we put 0 here, then we increment our I. Now, I is the same as J. We will put the value of J, which is 0 plus 1, so it's 1. And then, we increment both I and J. The I will be the start for the comparison of the pattern. So since the value of m here is 1, it means that there is already a prefix, which is the same as the suffix, so we will check the next point. Now is not a match term. To get the value of the I, what we'll do is to go to the value of the previous character in J, which is the 0. The time complexity to build this array is O of n. We already get the temporary array. Now, this array will help us do the substring search. Let us apply the substring search. Given the pattern and text, we need to know if the pattern exists in the text. What we usually do is start from the 0 index of the text and the 0 index of the pattern to compare. Since M and M is a match, we will compare the next letter in the pattern and the next letter of the text. Then next. Now, we compare that O here is not the same as X. Since we are not going to look back to the previous letters, we will check what is the next letter in the pattern to compare. So M here is same as well as N, O, M, and N. So now, we know that this pattern exists in the string. The runtime complexity for this algorithm is O of M, where M is the length of this text, and O of N, where N is the length of the pattern, so the total time for this algorithm is O m plus N.
Rabin-Karp substring search. In computer science, the Rabin-Karp algorithm or Karp-Rabin algorithm is a string searching algorithm created by Richard M. Karp and Michael O. Rabin that uses hashing to find any one of a set of pattern strings in a text. This is the Rabin-Karp algorithm for substring match. And here is the algorithm in checking if the hash of the substring and hash of the pattern is the same or not. In Robin Carp, we will use the rolling hash function to calculate and recalculate hash. First thing we do is generate the hash of a pattern. In our example, we will be using a prime of 3 to make it simple, but in reality, we should use a bigger prime number like 101. Also here, the value of A is 1, B is 2, and so on. But in reality, we should use the ASCII. Now let's calculate the rolling hash function. Let's say we were trying to calculate a hash for substring of length 3. We have A, B, E, D, A, B, C as a string. The value of A is 1, B is 2, C is 3, D is 4, E is 5, and so on. First is to calculate the hash of the pattern. The value of A is 1 plus the value of B, which is 2 times 3 raised to 1 plus the value of C, which is 3 times 3 raised to 2. We come up with 34. Now, we are going to take substrings of length 3 because the length of the pattern is 3 and see which matches the pattern. We start with A, B, E. The value of A is 1 plus the value of B, which is 2 times 3 raised to 1 plus the value of E, which is 5 times 3 raised to 2. That is equivalent to 52. So 52 does not match with 34. Now, we move forward and see if the next is matched. We will do the 3 steps process for B, E, D. Step 1. X is equals to odd hash minus the odd character. Step 2. X is equals to X divided by the prime. Step 3. New hash is equals to X plus prime raised to M minus 1 times the value of the new character, where M is the length of the pattern. Here is the algorithm in creating the hash. And here is recalculating the hash. Since we are only removing the A and adding the D, the process is we remove the value of A, which is the old character. Then we divide it by the prime number, which is 3. Then add the value of what has been added, the D, which is 4 times the prime number raised to the pattern's length minus 1, which is 2. Now we come up with 53. 53 is the hash of BED. Since it is not the same from what we are looking, we will move on to the next. Now let's get it for EDA. First, we subtract the value of B, then divide to the value of prime number. Then we add it to the value A times the prime raised to the pattern length minus 1. 26 is the hash of EDA, which is again not the same as the hash of the pattern. We will move on to the next. We do the same process for DAB. 25 is the new hash, still not the same to our pattern, so we move on to the next, A, B, C. So this number finally matches the hash of the pattern. Once we find the match, it means that the pattern exists in the string which is in the index 4. So this is how rolling hash works. So the time complexity for this algorithm is O of M and N, where M is the length of the pattern and N is the length of the text.
Z algorithm. Z algorithm has the same time complexity as KMP. The core of the algorithm is the function z of k. Z of k is where we are trying to find the longest substring starting at position k, which is also the prefix of the string. Left is the left bound of Z array. Right is the right bound of Z array. In this algorithm, we need to create a new string where its length is the length of the pattern plus the length of the text plus 1. Then, we need to add the characters of the pattern one by one into the new string. This $sign will separate the text and pattern. Then we will add the character of the text into new string. Now, we will call the function calculate with this new string which is going to return the Z array. Then we will iterate the Z array to look for the locations where the value of the Z array is the same as the pattern length. Then the result will add to the index minus the length of the pattern minus 1.
So this is how Z array is created. We have here this pattern. We are going to start where k is equals 1. Since k is greater than right, left and right will become 1. At this point, we will compare right and right minus left. We will compare the value of index 1 and index 0. Since it's not the same, what we do is right minus left, which is 0. So we put 0 here. Now we go back to the top of the for loop where k become 2. Now 2 is greater than right. Left and right becomes 2. We will compare right and right minus left. We will compare the value of index 2 and 0. Since they are the same, we will do right plus plus. Then we will do the process again. We will compare right and right minus left. We will compare the value of index 3 and index 1. At this point, they are not the same. We break the while loop. Now the z of k equals right minus left, which is 1. This means that at the index 2, there is a substrings, which is also the prefix. Then we do right, so right becomes 2. We do the process again, k becomes 3. Then same process again. We will compare right and right minus left. We will compare the value of index 3 and index 0. Since they are not the same, the z of 3 is 0. K becomes 4. Left is equals to 4 and so is the right. Then same process again. We will compare right and right minus left. We will compare the value of index 4 and index 0. Since they are the same, we do right plus plus so the value of right becomes 5. Then compare right and right minus left. Since they are the same, we will increment the right. Now we will compare this. Both of them are still the same, so right becomes 7. This time, it's not the same. We'll look for the z of k. Z of k is right minus left, so it's 3. This means that there is a substrings in index 4. Now we have our z box. Right becomes 6. Then we go back to the top of the for loop. The k becomes 5. Since k is lesser than right, we need to calculate our k1. k1 is equals k minus left, which is 1. Now we copy the z of k1 to the z of k. We increment again the k. Since k is still lesser than right, k1 becomes 2. Now at z of 6, we will go to the else condition, where z box is this. The left becomes k, which is 6. The statement is correct, so right becomes 7. We compare index 7 and 1. It is the same, so right becomes 8. Now we will solve for the z of k. Right minus left, so z of k becomes 2. Then decrement right, so it becomes 7 again. Now k becomes 7, and we will solve for k1 again. K minus left is 1. Now we copy the value of z of k1, which is 0.